Alright, hello everyone. So we're going to continue with practicing more ray diagrams. So I believe you guys already have some idea. We started with concave mirrors. So for an example, let's talk about the actually four different types of ray, the lines or the specific rays that we use to draw a ray diagram. So here we start with principal axis. That's the line that goes through the center of the mirror, and we mark a vertical line to indicate where the mirror is, and then here is the mirror, and then we mark F, and also we can mark C, the center point. So the rule is rule number 1. Light that comes parallel to the principal axis, so it's coming in parallel to the principal axis, it will reflect and go through F. So this has to be straight lines. So this is number 1. One that comes parallel reflects and goes through F. Number 2. So it is like there is some object over here. You can see there's an object here, so it's emitting this line. Number 2, we can say, let me see, use a different color. Nope, that didn't work. Okay. One that goes through F. One that goes through F. After reflection goes parallel to the principal axis. This is number 2. Goes through F, goes like this. Another one we can use is one that goes through C. Okay, I'll come to that in a new diagram. One that hits the center of the mirror. Center of the mirror. Oops, undo. Again, undo. You start from here. One that hit the center after the reflection makes the same angle. So whatever that angle it makes, it should make the same angle. So this is not a good diagram. Let me redraw this whole thing. One that hit the center reflects with the same angle. These angles are same. This is number 3. And then last one, fourth one. Light that goes through C reflect along the same path. Okay. So these are the 4 different lines we can use to create ray diagrams. And also you only need 2 at a time. Third and fourth one can be used as a confirmation, but just 2 lines are enough to make the ray diagram. Okay, so C. Alright. So let's try an example. Let's say you have a mirror with so this is concave mirror with let's say, let me change the color. how do I go back to the original color? Anyways, so let's say we have a mirror, f equals, let's go with 3 centimeters again, and there's an object. Let's not worry about the height, and you place DO, you place the object 5 centimeters. Alright, so how do we do? Draw the principal axis, mark the mirror, mark F. Now C is over here. You don't have to mark it all the time, but you can. If this is 3 centimeters, the radius of curvature or the center point will be at 6 centimeters. So the object is going to be somewhere over here. Light comes in, so we're going to use the parallel one, reflects through F, so that's 1, and I can use one that the center. Let's use a different color again, one that comes to the center. Make the same angle, reflection making the same, it has to be the same angle, reflects, and you just extend these lines until they cross each other. Where they meet, here we have an inverted image, actually a magnified image. Now this is your DO, right, 5 centimeters. This is your DI. You measure it from the lens, from the mirror to where the image is. That's your DI. So by looking at it, it looks bigger than DO, so maybe like 7-8 centimeters. You can measure it. If you draw it very accurately, you get very good numbers. So we did that, and another special case I want to show you is this one. F equals 3 centimeters. DO also, well, let's do 2 centimeters. Inside the focal point, right? Object distance is less than the focal length. So what happens in this case? Lens F, an object is over here. Okay, here comes parallel, reflects. This time we can't draw the one that goes through F, so we have to go with one that goes through the center, making the same angle. Now, as I said before, in order to see an image, light needs to come to your eye. So here's the object, here's the mirror, you are here, the observer is over here. So this is observer's eye, right? So somewhere behind or somewhere in the left side of this diagram, there's an observer. So it's not just these two light rays, right? There's millions of light going through. There's so many opportunities light can come to your eyes, not just these two. So somehow you don't have to be at the same place all the time. You just have to, you just need to have an observer in the room, right? So the light will come to the eyes. So these lines need to intersect at some point in order to create the image. So over here they intersect in front of the mirror. So we have this real image. If the image is in front of the mirror, we call it real. Also, by geometry, you can see it's upside down, and again by geometry, it's bigger than the object. So that's the magnification. It has a positive magnification, bigger than 1 magnification. Now in this case, the second diagram. Now so the person is watching, but you see that these light rays are diverging. They are not meeting over here, right? They are not intersecting each other. So what happens is our eye is going to extend them backwards until they meet. It is something we do. Our brain does. So it's going to extend this until they meet. They're going to intersect over here. And then, where they intersect, it creates the image. In this case, this is a virtual image. Why it's virtual? It is inside the mirror. It's on the other side of the mirror, behind the mirror. So there can't be anything real inside the mirror, right? It just appears inside. So these kind of images, we call them virtual images. So these concave mirrors are very versatile like that. Based on where you place the object, they can make real ones, virtual ones, upright ones, upside down ones. Now this is upright. This is upside down. You don't say USB, but you just say upside down. This is again magnified, positively magnified, means it's bigger than the object. So we'll come to all these properties soon. Alright. Okay. So let's talk about the other type, convex. How do we draw ray diagrams with convex mirrors? What is convex? Convex looks like this. Here's okay, convex. So the front side is over here, the back side this, and again we have the principal axis. Now let me redraw this thing. For convex mirrors, we define the focal point inside the mirror, right? So the focus or the focal point is over here on the back side of the mirror. So we say that this has a virtual focal point or a virtual focal length. The other one, concave, has a real focal point or a real focal length. This is behind the mirror, inside the mirror. So here's the focus. Now the light comes from the other side, right? The front side. Light has to be always from the front side. So let's say here we have an object in front of the mirror. You are standing in front of it, something like that. Here comes a different color. Here comes the parallel light. What happens? It reflects in an outward direction. Now again, if you think about concave, it's a converging kind of reflection, right? It tries to focus light into a single place. Over here, light kind of tries to go away from each other, such that appears like it reflects like this, but it appears like coming from this point. That's how we determine or figure out the direction of this reflection. It reflects outwards in a diverging way, appears like coming from this inside focal point. So think about another light beam, something, another parallel light. Reflects, appears like coming from this point. This is how they reflect. So there's another light over here comes in. Reflects, appears like coming from this one. So actual light is in front of the mirror, right? This side is the actual light. These are all just projections. We just project it using dotted line. There is no real light going into the mirror. It appears like it's coming from this focal point, reflecting from this focal point. So something like that. So this is the idea. We call these diverging mirrors because you see the light rays are going away from each other. So using this property, we can draw ray diagrams. So let's give a try. The black color is missing anyways. I don't want to mess with that. So let's try to draw a couple of ray diagrams. Alright. This time we draw it this way. Actually, hold on, let me read this. We mark F over here, and we can mark C over here. The same thing, C is 2 times F, it's still the same. Okay, so we place an object, let's say a couple of centimeters in front of it. Now let's see what happens to the parallel light. Here comes the parallel light, reflects as if it is coming from F. So this is 1. This is how the parallel light reflects. Light that comes to the center, that's always same. It reflects the same angle. This is number 2. Now where do we see the image of this thing? This is number 1 and number 2. These are the outgoing lights, right? They don't meet. Like we're looking at it from here. These light rays, they're not going to intersect over here. So this is already extended. This reflection we extend. This reflection we extend that also until they meet over here, and here we have a small image. This you can see it's small and it's most importantly virtual. It's inside the mirror. Okay, let's try another one. One second. So a third important light that we can use. So let's place an object over here. So we talk about number 1, the parallel one reflects such that it's coming from F. The one that hit the center reflects with the same angle, so these angles are same. The third one we can use, light that going towards the center, right? One that goes straight into the center. Now I'm going to try to connect this point and this point over here using one straight line. But here after this, like when I draw the line, it has to be a dotted line from this side. So like this. Not good. Not good. Okay. The line that looks like it's going to the center, once it strikes the mirror, it will reflect along the same path. That's the third one we're going to use. One that looks like going to the center. It doesn't go into the mirror, it reflects at this point, but it looks like if it is going towards the center, it's going to reflect along the same path. So in order to draw the image, let's use another one. Let's use green color one. One that hits the center, this point, reflects with the same angle. So we can extend this. And where they meet, here we have the image. Small image, virtual. Something it's very important to remember for convex. Convex. Images are always small. Always upright. Always virtual. When it comes to convex mirrors, there are no variations like concave. In concave, based on where you place it, it makes different kind of images, right? They can be big, they can be upright or upside down, big or small, real and virtual. But it doesn't happen with convex. It's always small, always upright, always virtual. So really doesn't matter where you place it, right? You can place it close to the mirror, like somewhere here, or far away from it. It will change this distance where it appears, but everything else is going to be the same. It's going to be a small upright virtual image. Because of that property, because of these properties, convex also have some nice applications. Again, can you think of an application? Probably you use these convex mirrors also every day, maybe. Not because, during the COVID, I'm not sure, but okay, before COVID, probably you have used, you have taken the service of a convex mirror on a daily basis, the weekdays when you're going to work. Alright, think about it. Okay, so we talk about concave ray diagrams, convex ray diagrams. Talk about the mirror equation in a little bit. Alright, thanks.